There she is, Fluffy the cat. Fluffy, say hi to the good people. Okay, anyways, here we go. We need an emergency session for success with regards to related rate problems. So, what we're going to do is we're going to say, well, let's talk about implicit differentiation at first. We need to find dy dx. We could take that equation, divide by 2, we get y is equal 5 halves x. So, the derivative of y with respect to x is 5 halves. Now, of course that's true. Whoop. Fluffy, good to see you, man. Get out of the way. Of course that's true because y equals 5 halves x, that's a line with a slope of 5 halves. So that tells us that y is changing by 5 halves every time x is changing by 1. So that's dy dx. But now let's do this same problem using implicit differentiation. So what we do is we differentiate the left side with respect to y, and then we convert that to differentiation with respect to x by multiplying by dy dx. And then the right-hand side, differentiated with respect to x, is 5. Well, then if we solve for dy dx, we divide both sides by 2, and we still end up with dy dx equals 5 halves. But wait a minute, let's just try for a second to wrap our brains around that. If we go back to the same problem, do we agree on the right-hand side you have to have x be multiplied by 5 to keep pace with what's happening when y is only being doubled? So how is y changing with respect to x? The left side only has to be doubled when the right side is quintupled. And so what's happening is y, the rate at which y is changing with respect to x is 5 halves. So hopefully that helps a little bit. If not, just follow the rules for doing implicit differentiation. Let's do a word problem. Let's do a related rates problem. We have a square that has sides that are increasing by 2 centimeters per second. Find the rate at which the area is increasing when the side is 6 centimeters. Clearly that's an S, okay? All right, so step 1, there's the formula that's going to relate area of a square to its sides being squared. So if we differentiate implicitly with respect to time, we get this right here. Well then, if we plug in what we know, we don't need to know the area at that time because we're not left with area in the formula. We're just left with how area is changing with respect to time. So we plug in the values that we know, and what we end up with is that the change in the area with respect to time is 24 centimeters squared per second at that precise moment when the side is equal to 6 centimeters. Now let's think about why does this make sense. If we were to look at what's happening to the square over the course of time, let's suppose at time 0 the square is 2 centimeters. Well, each side is 2 centimeters. You can see that the area is going to be 4 centimeters squared because area is two-dimensional. So it's going to be increasing at a faster rate than just the side because the measure of a side is one-dimensional, area is two-dimensional. At 1 second, the side is now increased to 4 centimeters. That means the area is now 16 centimeters squared. At 2 seconds, we now get to where we're at in this problem when the side is 6 centimeters and the area has increased to 36 centimeters squared. So we can see that the area is increasing at a faster rate than the one-dimensional side. At 3 seconds, we get this situation right here where the side is 8 centimeters and the area is increased to 64 centimeters squared. So why is it that our rate of change when the square had a side of 6 centimeters was 24 centimeters squared? Well, here it is. If you look at this, if you look at the difference in the areas between the 1 second mark and the 2 second mark, the area is increasing by 20 centimeters squared. Between the 2 second mark and the 3 second mark, the area is increasing by 28 centimeters squared. So right in the middle at the moment when the side is 6 centimeters, the average between what just happened in the second preceding that moment and the second following that moment, the average between 20 and 28 is 24 centimeters squared. So at that exact moment in time, the area is changing at a rate of 24 centimeters squared. Let's do one more problem. Let's suppose, the professor's back. How's it going, man? Anyways, let's suppose that we're trying to set a Guinness World Record for filling up a cone with a liquid. And we don't want to fail, so what we're going to do is the liquid is going to be Guinness beer. That way, nobody's tried it before. We know we'll be setting a Guinness World Record. But that's beside the point. Here we go. We've got this cone right here, and let's suppose we're told that the height of the cone is twice the radius, and we're told that the radius of the liquid is increasing at a rate of 5 centimeters per second. So what we want to know is, find the rate at which the volume is increasing when the radius is 12 centimeters across. So we're going to try to figure out how fast the water is filling up, what's happening to the volume at that moment in time when we're at 12 centimeters for our radius of the liquid, and we know that the rate of the radius is increasing by 5 centimeters per second. By the way, that means that the height of the liquid is increasing by twice that, 10 centimeters per second. Well, all we need to do is follow our steps. Step 1, go find the volume for a cone. That's the formula that will relate the three things: the volume, the radius, and the height. But we also know that the height is twice the radius, so we can actually substitute 2r in for h into this formula. So we can write it like this, so that volume is only a function of one variable. That's always a desirable thing. Now we're going to differentiate with respect to time, and that's what we get right there if we follow implicit differentiation. Now we plug back in what we know. At the moment in time, when 12 centimeters is the radius of the liquid in the cone, and we know that the radius keeps increasing by 5 centimeters per second, so we replace that rate of the radius increasing by that rate right there that we're given. All we have to do is multiply everything together, and we get that the change in the volume with respect to time is equal to this quantity right here. So, good luck, do well in the related rates problems, and we will catch you in class.